Okay, there are, I think, three things I wanted to talk about this evening. First one is the Liskov substitution principle. The second thing I wanted to talk about is the dependency principle, stable dependency principle. And the third topic from the lecture is the composite pattern. So there are three things. And there is the exam coming up next week. So I would like to spend some time talking about the exam as well. So that is a fourth thing. So let us first talk about the most difficult topic, which is the Liskov substitution principle. So what is Liskov substitution principle, or LSP? When I talk to some community faculty members, I got the sense that at least some people in the industry are quite interested in some of these design principles, and they are aware of things like the Liskov substitution principle, or LSP, and it is probably the most famous design principle in object-oriented systems, and certainly the most difficult topic, difficult design principle to understand fully. And it is possible that when you go for an interview, the person who is interviewing you might ask about LSP or the stable dependency principle or some of the other design principles. So I'm going to spend a little bit of time about talking about LSP now. It's all in the videos, I think, but still I would like to spend some time on it right now. LSP, the Liskov substitution principle, was enunciated by Barbara Liskov, who is a professor at MIT. And she talked about it a long time back. I don't remember exactly, probably in the early 90s or perhaps even in the late 80s. I don't quite remember. It was in a conference, the Object-Oriented Programming Languages and Systems. It used to be called OOPSLA at that time, Object-Oriented Programming Systems and Languages. But it has changed its name, I think, a little bit. But anyway, she gave that in a keynote speech. And her idea was this, or at least the problem that she looked at is very fundamental. When you have a class and you want to subclass it, are you doing the right thing? Is subclassing correct? Is subclassing appropriate? To give you an extreme example, which none of you will even dream of doing. Think about the library system. We have a book class, right? You all know that you don't subclass it as, you don't make book a subclass of member or a member a subclass of book. They make no sense. They're totally different things. So you wouldn't even dream of making one of them a subclass of the other. Or even some other examples, like if you think about a queue and a stack. A stack has a last in, first out principle, as you know, and a queue is first in, first out. So you don't make a stack a subclass of queue or a queue a subclass of stack. They are totally different kinds of things. You don't make a string a subclass of like button. I mean, they're different. But sometimes you get into difficulties. You start questioning, is this the right thing? For example, if you have a class called rectangle, is it okay to subclass it as a square? Can square be a subclass of rectangle? Those are more difficult to answer. So she came up with this basic idea, which I will share now. Okay. So suppose we have done this. Suppose we have a class B, and we created a subclass of it. Let me call it S. So B is the base class and S is a subclass of it. So base class and subclass. And we did that. And suppose we have a client. Client meaning a piece of code, Java code, that uses B and S. So the code is written like this. Say void I'm just giving an example, nothing else. B1, use B here, B1 here to do something. Okay, so I'm using an object of type B, at least the declared type. B1 is declared as B, right? This B1 has the declared type of B. And I'm using methods of B1 here to do some computation. It's not important what that computation is. The question is this: I could create an instance of S and pass it as a B, because every object of type S is also of type B. So when I do my computation here, the actual type of B1 could be B or it could be S. So then the question is, would there be some kind of an inconsistency, some kind of weirdness if I got an S as opposed to a B here? What do we mean? That is the kind of questions that she was trying to answer. So supposing you compute using an object of type S. Suppose we actually passed an object of type S and we did some computation. What Barbara Liskov said is that computation should have been possible for some object of type B, whose actual type is B. We got an S object, and is it possible that there exists some object of type B that would produce the same behavior? If so, S is of type B. For example, if this is rectangle and this is square, B is rectangle and S is square, I'm assuming that everything is a rectangle, but when I get a square, would I be able to say, oh, okay, this would have produced the same result for some rectangle? Then a square is like a rectangle. That is the idea she had. It was a very fundamental concept that she came up with. And she then, I mean, that was brilliant. But then how do you decide this? How do you know that this subclass object will behave like some superclass object? I mean, obviously, we cannot come up with all possible client code and examine it. There are infinite number of them. So that is ruled out. So what she set out to do was work on answering that question, whether there will be an acceptable behavior for every square. That is, for every square, we can get a rectangle that will produce the same behavior. Or for every S, there will be some B for which there will be a behavior that is identical. So for that, what she did was she came up with a paper that looked at class declarations and came up with a set of conditions that said, okay, if you have this and such things are satisfied by the classes, then things are going to be okay. So that is a very difficult paper to understand. I have read it multiple times, but I probably have understood 80% of it. It's really hard. It's probably the hardest paper that I have read in my life. Okay. In any case, that has been influential in the design of Java to some extent, as far as I can tell. I will tell you some of the things that, or at least one of the things that LSP talks about and are also reflected in Java. Okay, so let's look at Java. Right? Suppose we have a class B and a class S extends B. And suppose I have a method here, public void m. No, I don't want void here. Public, let's say p m, and let's say I have a parameter of type x, and I do something inside. It doesn't really matter what I'm doing. And here, suppose I try to override m. So I'm going to override m. The question is, what can I put here and what can I put here for the type? So some parameter, let's call it, I don't know, let's call it x2 maybe, all right? So what can I put for the type of x2 and what can I put for the type of p? Assuming that I wanted to override m. So I wanted to override this method. So I need to put a return type. I need to, of course, the method name is going to be m, as you know. This parameter is of type x. What can I put for a parameter here? Well, in Java, the rule is this. If you put x here, you have to put x here. There is no choice. If you're overriding, the parameters have to have exactly the same type. This is returning a p. What can you put here? The answer is p or a subclass of p. So you could put p, or you could put anything that is a subclass of p. So if it is like this, any subtype of p is fine here. So I can put q, I can put r, I can put p, but I cannot put, so let me put something like a here. I cannot put a here. The idea is that when I execute m, it will not produce anything that this cannot produce. M can only produce P or subtypes of P. So this will only allow M in S to produce P or a subtype of P. So that is why this can be P, Q, R, or anything below. And here, M accepts X's, things of type X. And Java requires that you accept things of type X. But this is a little different from what LSP says. In LSP, this can be anything that is a superclass of X. So if you had R as a superclass of W, which is a superclass of X, you can put X, W, or R. The thing is, M in S is as generous, if not more, than the M of B. So LSP is a little more general than what Java is allowing, but there is that basic stuff which perhaps they borrowed from LSP. But as I said here, Java is more restrictive in terms of parameters. And there are similar kinds of things that LSP requires for base classes and subclasses to say. What we have talked about are post conditions and preconditions. But there are lots of other things that LSP talks about, which we are not going to discuss in this class. They are beyond the scope of an undergraduate class, in my opinion. Okay, so that is what I wanted to talk about regarding LSP. So if anybody asks you in an interview as to what LSP is, what you should say is this: it is a way of checking whether a certain class is a proper subtype of some other class. That is, if S is a subclass of B, is that hierarchy proper? LSP answers that question by using a pretty hard to understand theory. And one of the things it requires is that the return types have to be no more general than the return types of the superclass methods. The parameters have to be as generous as the parameters of the superclass methods. The exceptions that you throw here have to be, in the superclass, have to be at least as generous as the exceptions thrown by the subclass methods. If this superclass method doesn't throw any exceptions, you can't throw anything over here. And there are things about the properties, that is the fields and all that, which are probably a little more difficult to understand, and execution sequences, etc., which, as I said, we are not going to cover. So any questions on this? Okay, if there are no questions, let me stop this sharing and then talk about the next topic, which is about dependencies. So I wanted to bring your attention to one of the tables that was in the document I had uploaded for the lectures. So let me share that. And this won't take as much time as the LSP discussion. Okay, you can see this table. This is listing all the application packages of the drawing program. Okay, probably some 10, 15 packages, I don't remember the exact number. And all those packages are listed here as well as columns. And I only consider classes. Okay, so in the package controller, how many classes of other packages does or do classes here depend on, use? That is, for example, this says, according to this table, the number of classes in controller that depends on, or the number of classes in controller.commands that are dependent upon by classes in controller is 1. Or the number of classes in the model package dependent on by controller classes is 1. So there are 2 classes outside of this package that classes here depend on. So this is the total. And if you add, so you can make a similar interpretation for all this. And I wanted to comment about this one, controller.states. This says that it is, there are 2 dependencies. There are 2 classes in GUI.view.views that classes here depend on. That has been changed. Now this is actually 0, because this table was created last semester. Then I realized I had to change the drawing program. I didn't want the logical controller to be dependent on a physical controller. So I eliminated this. So this is now 0. But you can see that controller.states depends on a number of classes. The total number of dependencies like 51, etc., etc. So you can see lots of those kinds of dependencies. And so if you add up things in the vertical column, these are the things that, this is the number of dependencies from other packages that or this is the number of dependencies on this package from other packages. So you can use these two to compute the stability of a package. Okay. If the stability is 1, then that is highly stable. For example, controller.events doesn't depend on anything else, so its stability is 1. Whereas something like controller.states, you can see that stability is 0.05. But that is somewhat misleading, as I have written in this document. Controller.states stability, according to this measure, is 0.05. So that is actually a misleading statement. So this is not a perfect measure, but it gives you some idea about the goodness of the design. Okay. So stability of 0 is considered, stability of 1 is very good. This was actually suggested by a person named Martin. But many of the measures that you come up with in these kinds of situations are not perfect. They are, I mean, you can look at them and then maybe use them to some extent, but that they may not tell the whole story. Okay, that is the second thing I wanted to say. Now, the third topic that I wanted to talk about is the composite design pattern. So for that, what I am going to do is create a blank document and a Word document and show you that. Okay, so here is a Word document. I'm going to create a bunch of shapes here. So I'm going to say insert and then go to shapes. So let me put in a rectangle. Then let me put in maybe some other shape, a circle. Then perhaps one more. Yeah, triangle. Okay, so I have 3 shapes. Now, you all know this kinds of things, but I can click on multiple things. I'm on a Mac. I pressed shift and clicked the mouse once again. I am pressing shift and then clicking the mouse. So I am able to select all of them. Or I can select some of them, not necessarily all of them. And then I can move them around. I can delete all of them. I can undo the thing and they all come back. They all came back. I can right click and then say group, and they are grouped into one unit. Now I believe I can even save this and it will remain as one unit. So what I am doing is I am collecting a bunch of shapes and then treating it like a single shape, right? So how do you do that? For this, we use the composite design pattern. A composite is a class. I mean, you can call it whatever you wish. You can call it maybe composite shape. That would be a subclass of shape. So it has all the properties of shape. And it also has a collection that contains the individual shapes. And it can actually be a hierarchy. You can, for example, I suppose this is possible. I know that this is possible in Word. I can create new shapes here. Let's say something that looks different. A couple of them I will make. Okay, so I created two more shapes. Now I can click on these two, select those two, and then say group them. I group them into, so I have two groups now. This is one group, this is another group. So this would be one composite shape, this would be a second composite shape. Now I can select these. I think I have selected both. Now let me see here again. Let me do this again. Yeah, I selected both of these. Now I can group them together. So this is one more composite shape. So I have three composite shapes. One using these three, that is one composite shape. The second composite shape has these two. Then the third composite shape has these two smaller composite shapes. Now I can move them all together. Or I can, if I don't require them to be a single composite shape, I can right click them and then say ungroup. Then they get split into two. So I have two composite shapes now. So this is a collection. A composite is a collection, but it is also a subclass of shape. So if you ask a composite shape to move, for example, it move. Oh, okay. If you move a composite shape, what it does is it moves all the individual items, all the individual shapes, because it has the collection. So it would iterate through the collection and perform move on each of these. That is how it is actually implemented. If you want to change the color of a composite shape, what you will do is you will specify the color, and then the composite will iterate through the collection of shapes and change individual colors. So that is how the trick is done. Okay, so it is a very useful design pattern when you have to do these kinds of things in your object-oriented program. So that is a summary of the composite shape. For the exam, I expect you to understand what a composite shape is, but we haven't really gone into depth into this pattern using Java code or anything. So I'm not asking you to be an expert in writing code, but you should understand the principles behind that. Any questions before we get into the discussion of the exam? All right, let me then share the exam document. I just uploaded it a few minutes ago. It should be under exam 3. Information about exam 3 should be under the folder exam 3. So this is that document. This will be next week at 6 p.m. It's for about 3 hours, like the previous 2 exams. And it will only cover stuff starting from finite state machines through whatever we are covering this week. Nothing else. There will be 3 sort of long questions. Long meaning you have to write Java code or you have to do some other work. The 2 programs will ask you to write Java code. And there is a third problem where you'll have to actually come up with the finite state machines, with a finite state machines state transition table. So you'll be given a scenario and then you'll have to come up with the state transition table. Then there will be some multiple choice questions or select true false kind of multi-select, those types of questions for a total of 20 points. So not like 50 points in the previous 2 exams. So we will be covering the FSM approach, the MVC pattern, all those design patterns like bridge and state and observer, composite, etc. The drawing program, over design principles. One of the questions would be to modify code in an existing implementation for a finite state machine. So you'll be given a state transition table. I will explain the problem in the question, and then you will be given an implementation. You need to add missing code. Okay, so a large part of the code you don't have to touch. You only have to modify certain part of the code so that the program will work as specified. That is the first question, or one of the 3 questions. A second question would be to introduce a new shape to the drawing program. And the design and implementation have to be very consistent with the design and implementation of shapes in the existing drawing program. For example, for the new shape, there has to be a button, like there is a button for polygon, like there is a button for line, and so on. It should be possible to do undo and redo. It should be possible to save and retrieve the shapes along with the others. So the appearance should be consistent. You should not modify things unnecessarily. You just have to add things where they should be added because you're introducing a new shape. You cannot assume that there is some other shape here, so I'm going to use I'm going to call some methods in existing shape classes to do my work. That kind of cutting corners is not accepted. The third one doesn't require any programming. You'll be given a situation and you need to come up with the finite state machine for that, the state transition table for it. That is the third problem. Okay. Any questions before we go to the class exercise? Tonight's class exercise is not going to be very long. I think you probably would require about an hour and a half. Okay. But some of you might take longer, some of you might take less time. So what I'm trying to say is there might be some time for you to work on your project. Any questions before we do the class exercise? All right, let me then stop recording.